So here we are, continuing our trek through Unit 6, which is Energy Resources and Consumption. We have talked about the traditional energy sources that we use, fossil fuels. Now we're going to look at the conventional energy alternatives, and then that'll segue us into the new energy alternatives. So we're going to talk about reasons why we should be seeking energy alternatives. We're going to look at how those conventional alternatives have contributed to world energy supplies. We're going to look at nuclear, look at how we use nuclear power, look at the pros and the cons, as well as the societal debate related to nuclear. We're going to look at bioenergy and hydroelectric power. So those are our three conventional energy alternatives: nuclear, biomass, and hydropower. So more than 80% of our energy supply in the world comes from coal, oil, and natural gas. So if you add these up, coal, oil, and natural gas, you get more than 80%. And 2/3 of that, coal and natural gas and oil together, are used to generate electricity. The fossil fuels, as we well know, are non-renewable and limited in supply, and they have known environmental impacts when we use them. So we're looking at alternatives, and these are your alternatives that we're going to talk about: bioenergy, nuclear, and hydropower. New renewables are the next chapter. They're considered conventional alternatives because we have used them. The technology is well established. They're used pretty widely. They have less impact than fossil fuels, so they are a good solution for now. But they have more impact than some of these new renewables that we're going to talk about in the next chapter. So that's when we talk about currently used renewables, conventional alternative, we're talking about nuclear, hydropower, and biomass. Okay. It plays a bigger role in electricity generation, okay, than some other energy forms of energy use. So nuclear, hydro, and bioenergy are a decent part of our energy consumption when we talk about the conventional alternatives. So let's talk nuclear. We have the greatest nuclear electricity production, right? We produce 100 gigawatts of nuclear power. So nuclear power is when you use the energy in a nucleus to generate electricity. France uses the most. Okay, almost 72% of their electricity is generated from nuclear power, followed by Ukraine, and we're going to talk about why that is in a little bit. So nuclear energy is the energy that holds the nucleus together. So let's do a little chemistry review. The three subatomic particles are protons, neutrons, and electrons. Electrons are around the outside, right? Zipping around in their orbits. The nucleus is the protons and the neutrons, right? So it's the energy that holds these protons and neutrons together that we harness when we use nuclear energy, okay? So a nuclear reactor is where the actual reaction takes place, this reaction that we're going to talk about. That reaction is a fission reaction, okay? So what happens in a fission reaction, you have these radioactive isotopes, which we're going to talk about in a minute. Uranium is one of those. There are neutrons that are shot at, that are released and bombard these nuclei of uranium-235. When that neutron hits this nucleus of uranium, it breaks it apart. When that break happens, okay, when the bigger nucleus breaks into smaller nuclei, energy is released. Okay, so you've got these two smaller nuclei that are produced, and then you have these free neutrons. that are loose, running around, bopping around in the reactor, that are then available to hit more nuclei of uranium to make this process continue to happen. We're going to do a little math related to half-life. It's the amount of time it takes for half of the atoms of a certain element to give off radiation and decay. So left to its own devices, uranium-235 will naturally break down to make these two smaller atoms, right? So the amount of time it takes for that to happen naturally is called its half-life, okay? So uranium, how do we get uranium? Nuclear energy is considered non-renewable because uranium is mined from ore in the earth, okay? So there's only there's a finite amount of uranium ore in the earth. So that's why we consider nuclear energy non-renewable. All right, so that uranium gets mined and it's got to get processed, okay, and worked and reworked until at least 3% of that sample is just uranium-235. And then that uranium, that ore that you get, is then put into little pellets, probably maybe about the size of your thumb, pellets of this uranium oxide, which is the mineral, and then it's put into metallic tubes called fuel rods. Inside the reactor itself is a moderator, which helps to slow down the reaction. And then there are control rods that are put into the reactor core to moderate, to control the rate of the reaction. Sometimes they will, if you want the reaction to slow down, you will put the control rods in so they absorb the neutrons so those neutrons don't hit nuclei as much. And if you want it to go faster, you pull the control rods out so those neutrons have more of an ability to hit nuclei to allow fission to take place. So the energy that you see as the result of fission is heat. The heat creates steam, which turns a turbine to generate electricity. And let's just look at the picture. It's so much easier, okay? So here's the reactor core, usually lined with lead or something like that. All of this reaction takes place in a containment building because if there's any leak of radioactivity, it's pretty well isolated, okay? So you've got the reactor core, right? In the reactor core are the fuel rods, these little things right here. And the control rods, these guys, the taller ones that you can move up and down to control the reaction. And the moderator, which is usually water. Okay, so you have, this is where the fission actually takes place. Okay, so depending on the rate of this reaction, the rate of the fission reaction, in the reactor core, if you want it to go faster, you pull the rods out. If you want it to slow down, you put the rods in, okay? These control rods are what absorb the excess neutrons, all right? So all of this fission is taking place, all of this energy is being released. The in and around this reactor core is water, right? So that heat heats water to make steam, right? Which then will cool down and come back. So this loop, the primary loop, cycles. The primary loop goes through the secondary loop, right? This water moving through the primary loop is radioactive because it's in contact with the uranium fuel, right? So this loop has to be isolated from the secondary loop. So the warm primary loop heats the water in the secondary loop. Remember, we looked at the coal-fired power plant. In this case, this is where you get the steam to turn the turbine to generate electricity, okay? That water from the secondary loop needs to cool down. Again, it's the same idea, running through a condenser in the cooling tower. And then that cools down to go back through the secondary loop. It's really important to keep the secondary loop water isolated from the primary loop water. And they even keep the condenser water isolated from the secondary loop water, just in case there's any radioactive leak. So if you look at pros, some of the pros and cons of nuclear energy, you get anywhere between 4 and 150 times fewer emissions than fossil fuels, okay? So if you live in the shadow of a nuclear power plant, there's way less air pollution. So you're way less susceptible to those diseases that we've already talked about related to air pollutant exposure, all right? So it's a really good thing. Reduces air pollution, reduces emissions of carbon dioxide. It's a good thing. There are drawbacks, okay? The waste, we're going to talk about this, stays radioactive for a while. And then there's the potential accident, potential for an accident at the plant. You know, the risk of disaster is small, but if there is a disaster, the disaster is catastrophic. So if you look, if you do a cost-benefit analysis, you look at the pros and the cons, a lot of governments see nuclear power as advantageous as compared to coal, right? It's mostly because of these issues. They take a look at the radioactive waste and the potential for an accident and say, it's not that big of a deal. All right, so if you look at the red is the bigger risk, right? So if you look at issues related to ecosystem disturbance from mining the material, it's more extensive for coal. You look at greenhouse gas emissions, a lot more greenhouse gas emissions from coal than from nuclear. Air pollutants, you got nothing from nuclear, and there's a whole lot of stuff that comes from coal. Radioactive emissions, there are no appreciable emissions from coal, and really there are no appreciable emissions during normal operation in a nuclear power plant. However, this is the part that gets everybody. There's a possibility of emissions during a severe accident, okay? And we're going to talk about 3 incidents in my lifetime, and I'm not that old, where there have been emissions of radioactive material. In terms of occupational health, there are more known health problems and fatalities from coal mining than from nuclear. And nearby residents, you know, you get a lot more air pollution from coal, and there are no appreciable known health impacts under normal operation for people living in the vicinity of a nuclear power plant. Again, assuming everything is operating normally. Okay, we got more. No widespread effects if there's an accident or sabotage. Here's your catastrophic widespread effects if there's an accident or if somebody does something on purpose to a nuclear power plant. There's more solid waste generated for coal. There's a lot more radioactive waste generated for nuclear, which makes sense. Coal should last us for several hundred more years, but we really don't know how much nuclear material we have available. It could be more, it could be less. So the other side of things, it's a dream at this point, is nuclear fusion. If fission is splitting the atom, fusion is putting atoms together, okay? So in the process of fusion, which actually takes place during the sun, or in the sun, and it's what gives us the energy and the heat from the sun, hydrogen, okay, hydrogen 2 and hydrogen 3 are fused together, right, are mushed together to create a whole lot of energy, and helium and a neutron, okay? So if you look at the material that's left after nuclear fusion, it's helium, neutron, and energy, okay? There's a lot less hazardous material, and helium at Earth temperatures is so light that it can just escape our atmosphere, right? So we wouldn't have necessarily a buildup of a whole lot of helium. But in order for it to happen, you need conditions that are similar to that of the sun, okay? So you need temperatures in the range of millions of degrees Celsius, okay, and a whole lot of pressure. And they have tried to simulate nuclear fusion at the Large Hadron Collider. I believe that's in Switzerland, or it's in the Netherlands. It's somewhere in Europe. And they've been successful, but it's taken a lot more energy to go in than what they've gotten out. So it's a negative energy return on investment. Okay. So that's why we haven't done that yet. We're working towards that. So these are the 3 accidents that have taken place in my lifetime. And these incidents have really given the public a lot of hesitancy and anxiety over the use of nuclear power. Okay. So 3 Mile Island was 1979. I remember it. It was near Harrisburg. And there was an accident that was a result of human error and a mechanical failure that led to the water draining out of the reactor vessel. When the water drains out of the reactor vessel, that reactor core, it does not allow for fission to take place at a moderated rate. Okay, fission gets out of control, right? And it creates something called a meltdown, where those fuel rods started to melt and then caused a lot of radiation to be released. That fission reaction was not controlled, was not moderated. So it went a little crazy. And we'll give an example when we do our key points of what that actually looks like. 3 Mile Island didn't cause a full meltdown. The radiation was contained. I really clearly remember my parents watching the Philadelphia news and everybody worrying a lot about what was going on at 3 Mile Island when I was a little kid. They were really, really worried about what was going to happen. This I really clearly remember. I was almost 11. In 1986, an explosion at their Chernobyl power plant in Ukraine caused a huge explosion and radioactive debris to go up into the atmosphere for 10 days. It was Soviet Russia. They really were not very forthcoming with details and information for the world in general, because it was a communist nation at that point. They didn't want to show any weakness, especially to the United States, because we're in like mid-Cold, we're like in the throes of the Cold War still at this point in 1986. So there was a lot of denial and a lot of, people saying, oh, everything's fine, everything's fine. So 31 people were directly killed as a result of the explosion. And then there were thousands more that were sickened or wound up developing cancer as a result of the radiation exposure. We will watch at least one episode of the HBO miniseries Chernobyl, and then probably parts of the last episode. So you can kind of see, it's dramatized, but it really gives us an idea of what happened. It's a really good miniseries. I totally recommend that you watch it. So fallout from Chernobyl carried really strongly across the northern hemisphere, in Belarus and into Russia, through areas of the Ukraine. They knew something was up because they, at a nuclear power plant in Finland, people would go through the Geiger counters, like a scanner, to see their levels of radiation before and after they were in the nuclear power plant. So if they were power plant employees, they got scanned on the way in, should be clean, and then got scanned on the way out. So people were walking into the power plant in Finland, and they were setting off the Geiger counter, the sensors. So they knew something was up, and they figured out where it came from. So they built a big sarcophagus, to kind of like a tomb to entomb it. But then they have since built a larger containment dome. It was the largest moving structure on the planet when they built it. I think it popped into place in 2018 or 2019, pretty recently. So now the levels of radiation exposure have gone down tremendously with the building of this thing. So here's the third one, and this is relatively recent. In 2011, there was a huge earthquake that hit off the coast of Japan. And, you know, Japan is a tectonically active area, and it sent a tsunami towards the east, towards the eastern shore of Japan. So it was off the east coast. It was underwater, and it sent the tsunami wave towards the Japanese coast. So in Japan, along the coast, they have a power plant called Fukushima Daiichi, and the earthquake shut down the power. But as is the case, which would make sense with nuclear power plants, there's a lot of redundancy. So there's generators. So that was fine. You know, the earthquake knocked out the power. So the generators kicked on, but the tsunami came in and flooded the generators. Okay. So when that happened, there was no way to pump water into the reactor cores, and there was no way to get the control rods to move. So we started with a meltdown. Radioactivity was released. Even though radioactivity was released, it was lesser amount than what you saw when Chernobyl was released. And people have since evacuated. They're starting to come back. It's been quite a few years, more than a decade, but they're still starting to come back. And there are people that are continually screened for the effects of radiation, different kinds of cancers and whatnot as a result. So the winds in this area blow towards from the west to the east. So a lot of the radiation wound up in the ocean. Okay, although you did detect trace amounts around the world. Again, this is the same isotope. So we were able to identify it as it moved throughout the world. A lot of it fell into the Pacific Ocean. A problem with that is that fishing is a huge industry in Japan. So Japanese fishing fleets went out and caught these fish that were in this radioactive water. So we still don't know, a decade later, what the long-term health effects of that contamination were. There have been smaller scale incidents that don't make the news because, safety measures have prevented meltdowns from happening. Another big concern with nuclear power is that radioactive material, the spent fuel rods, once they can no longer generate electricity, are used, for fission, they're still radioactive. If they're not carefully monitored, one of our big fears in the United States is that they could be stolen from power plants and used in a terrorist attack. And we've also been working hard since the end of the Cold War to reduce stockpiles of nuclear weapons for that same reason, and turning that material into uranium to be used at power plants. So instead of mining more ore, we're going to use the resources that we have. What do you do with the waste? Even after it's not useful anymore in the generation of electricity, it is still radioactive to the point where it can cause damage if exposed to humans. Its half-lives, okay, it's going to be radioactive for hundreds of millions of years. So it's not like you can just bury it in the ground. It's still going to be radioactive. So we do one of two things with it. We put it in wet storage, and right here, this is what the fuel rods look like. It's a bunch of little rods in a bigger casement. So they keep them in wet storage. As we know, it's water, so it tends to slow down the reaction. Or they put them in these big, giant casks. Okay, there's a guide for scale. So 12, 15 feet tall, that are lined in lead and made of steel and concrete. And they're buried underground in geologically stable areas. Okay, so those are two ways we can deal with that waste. They are spread, those fuel rods are spread throughout 120 sites in 39 states. it causes some concern for people who are managing that waste at these power plants, because that's a lot of opportunity for people who want the nuclear fuel for nefarious reasons. You know, there's a lot of opportunities there, rather than put it in one spot, right? So have one central repository for all of this nuclear waste, so that it can be heavily guarded in one spot. So in Sweden, they selected a power plant to be the central location for the storage of nuclear waste in one spot. It's buried way, 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 way underground, as you can see, and they put it in copper canisters, and it's buried in the bedrock. We had a facility planned. They were still debating it when I started teaching, you know, close to 25 years ago, at a place called Yucca Mountain in Nevada, but people didn't want that in their neighborhood, you know, a high-level nuclear waste dump, essentially, in their yard. And then there was a lot of issues related to the transportation of that nuclear waste from all of these sites to here, to Yucca Mountain in Nevada. So, like, you would have to hire guards, and would you ship it by rail, or would you ship it by truck? Would you take it by plane? There's lots of expense for that. So between the protests and the safety issues regarding the movement of that nuclear waste from its origin to Yucca Mountain, they decided to scrap the project. Since 1990, nuclear power has not grown very fast, mostly because of the anxiety around these disasters in human memory. It's really expensive to build a nuclear power plant, and it takes a long time. They are not lasting as long as they should have. They were expected to last about half the time. So if they project that a power plant can operate for, 40 years, it's only operating for like 20. So that's problematic. And once you have power plants that have aged out, it becomes very difficult and very expensive to decommission them, to take them apart. Okay. So all of those things aside, it's still one of the most viable alternatives to fossil fuels. We have the technology. They're also looking at these, a new generation of reactor. So it's small and it's modular. So it's prefabricated. It's like cookie cutter, and it can be installed individually or in combination at power plants, depending on demand. So it's like the next generation nuclear reactor. Okay, so it's more efficient. It reduces radioactive waste, right? The safety features are more enhanced, and it's less expensive to build and implement. So if you take a look, here's your fission, right? Fission at the reactor core. Your control rods move up and down. The coolant, water heated by the core, will then transfer to your secondary loop, and then you will generate steam to turn the turbine to generate electricity. So there's a cap on it all, the pressurizer, that keeps that water from boiling. So it keeps everything under control. So there is new technology for the nuclear reactors. It's interesting. Okay, so that's nuclear. We're going to talk about bioenergy or from biomass. So bioenergy comes from biomass. Biomass is any organic material that's derived from living or recently living organisms, and it contains that chemical energy from photosynthesis, right? So you've got bonds of carbon between, in the form of sugars, okay? So in theory, bioenergy is renewable, all right? So as long as you can grow the plants and you don't use them faster than they grow, it's going to be renewable. And it doesn't release any net carbon dioxide into the atmosphere. This is important. Burning biomass, if you burn a plant that has done photosynthesis, that plant has taken carbon out of the atmosphere. All right? So there's been a shift from the atmosphere into the biosphere. When you burn that biomass, you're taking that carbon in the form of carbon dioxide out of the plant and putting it back into the atmosphere. Okay? You're just shifting it back and forth between the biosphere and the atmosphere. The problem with fossil fuels is those fossil fuels have been stored in the geosphere for the course of hundreds of millions of years, right? So when we burn the fossil fuels, we're taking the carbon from the geosphere and putting it back in the atmosphere. Okay, fine. If it was going to be no net release in carbon dioxide, then that carbon would have to come back into the geosphere, and it's not happening fast enough. So as long as you're more careful with how you burn biomass, right, or how much biomass you burn, and you grow the same amount that you burn, you should have no net release of carbon into the atmosphere. So where do we get it from? Trees, charcoal, crop residue, and you can even burn animal waste to a degree. So direct combustion, you can cut down wood from trees if you have a fireplace, pellet stove, that kind of thing. You can burn charcoal or animal manure, dried animal manure. So if we're going to use biopower for electricity, you can burn crop residue like corn stalks or sugarcane stalks. You can burn wood waste from logging, the sticks and stuff at power plants. You can use landfill gas, which is produced as a result of decomposition. You can use livestock waste to generate methane in anaerobic digestion. You can use corn and sugarcane residue for making ethanol. You can grow crops for biodiesel. You can use cooking fuel for biodiesel. They're also looking at growing algae for biofuels. So there's a lot of ways that we can use biomass. In rural regions, this is super important. In the developing world, people tend to rely heavily on biomass, fuel wood in particular, like you can see in this picture here, because it's readily available. And we talked about this when we talked about the forests. When you use what's there, it's the cheapest, most available fuel source for cooking and heating homes, and lighting too. But if you use it too much, then you're going to lose forest, right? Lead to deforestation, which leads to soil erosion, which leads to desertification, okay? So that's in rural areas in developing countries, that's why deforestation is happening at a higher rate, because it's what's there. In the developed countries, like ours, we use bioenergy to make biopower, right, to generate heat and electricity. We can also use biomass to create liquid biofuels, like ethanol and stuff that we talked about. You can use waste materials from logging, like these scraps, sawmills, pulp mills, paper mills. You can burn that as a source of biopower. And we talked about the biogas as well from decomposition. And there's an example of a biogas plant in Sweden and how they use it. So it's got a lot of additional applications. So you can grow crops specifically for biopower, for using biomass, grasses that grow quickly, bamboo, fescue, and switchgrass. And then you can do the co-firing method to allow to burn biomass in addition to coal. In terms of impact of biomass, it contributes less to climate change, and typically it's more sustainable than burning fossil fuels because you can always grow, more fescue or bamboo or corn or whatever. But the downside of it is that when you cut these plants and grow them and use them for fuel generation, you deprive the soil of the natural decomposition and the putting of those nutrients back into the soil that would happen if the plant were to naturally die. So ethanol is one of the fuels that we can use. It's produced by fermenting crops like corn, and it's pretty widely used in the United States. And we use corn mostly for that. It has reduced a lot of our auto emissions. Here's what you see, okay? Flex fuel vehicles can use 85% ethanol and 15% gasoline, right? So it reduces a lot of the carbon emissions that come out of tailpipes in the flex fuel lines. And they do it a lot in Brazil, where they take sugarcane residue and create ethanol. It's not our most sustainable energy choice if we're going to use biomass, because if we're going to grow corn for this use, it's going to create other problems. It's going to increase the use of fertilizers and pesticides. We're going to use groundwater to grow the crops, and we're going to use fossil fuels to allow industrialized agriculture to grow this corn. And it takes a whole lot of land. We would need to expand our corn acreage if we were to move to ethanol in the United States by 4 times. So that's quite a bit of additional land dedicated to ethanol, growing corn for ethanol. So biodiesel is one of the fuels that you can use to move your cars down the road. They create it from vegetable oil, used cooking grease, or any animal fats. When you go to like a fast food restaurant, you'll see that their grease dumpster typically has a lock on it, because when biodiesel first became a thing, a decade ago or more, people were going to the dumpster, the waste oil dumpster, and siphoning it out to get the oil, the used cooking grease, to make biodiesel. They were stealing it. So, they've since locked that down. Biodiesel has a whole lot of advantages. You can see them here. It's non-toxic, it's biodegradable, it's cost-effective. You can use food waste, and it's got a nearly identical fuel economy. So your car is going to get the same mileage on biodiesel. Okay, if you replace biodiesel, if you replace regular diesel with biodiesel, you're going to reduce a whole lot of emissions from diesel engines. And a lot of our locomotives and a lot of our transport trucks run on diesel. So that would be a good thing. We talked about this earlier. They're looking at using algae, growing algae either indoors to use to generate biofuel. Okay, so biodiesel, ethanol, or even jet fuel, which would be a definite reduction in the carbon footprint of these methods of transportation. Is it carbon neutral? Yeah, in theory, yes. But that only holds true if we don't use forests, okay? If we use the grasses and the other kinds of crops for biomass. Okay. The last kind that we're going to talk about is hydroelectric power, or hydropower. We kind of talked about this before when we talked about water usage. It uses the kinetic energy of flowing river water, right? So the kinetic energy, it falls from the reservoir down through the dam, turns it into mechanical energy, which turns the turbine, which turns it into electrical energy, okay? So here it is. Most dams use the storage technique. So the dam runs across the river, and there's a difference in height. So there's your kinetic energy. It's the energy of falling water. So the water goes into the dam and then mechanically turns the turbine, which will then turn it into electrical energy, right? So the water will fall through and head down river, okay? And then that electricity is transmitted through power lines. The other kind of dam is the run-of-river dam. So instead of blocking the river altogether, there's a pump that diverts some water out of the river, and then that water falls into the powerhouse, which turns the turbine, which generates electricity, and then the water falls back into the river, okay? It doesn't disrupt the natural flow of the river as much, and doesn't have those ecological impacts that we talked about in chapter 15 when we talked about dams for the first time. The amount of water that you get, the amount of electricity that you get from a hydropower plant is directly determined on the volume of water that moves and how far it moves. So the more water that flows through, the higher the difference between the reservoir and the river, the greater the chance of, the greater the electricity you're going to wind up having. So the third kind that we're not going to really talk about too much is this idea of pumped storage. So you move it from a lower reservoir to a higher reservoir when there isn't a whole lot of demand for power, and then when power demand goes up, you open it and let it flow back down the hill. But I really don't know if there are any dams currently in use that use that. It's clean and it's renewable. So there are some really big advantages over fossil fuels. It's completely renewable. As long as you have water flowing, you're going to have hydropower. It's efficient. It's got an amazing EROI, 80 to 1, which is really great. And you don't get any pollutants. It's just falling water, turning the turbine to generate the electricity. But there are issues, like we talked about in a previous chapter. The riverside forests, the riparian habitats, upstream are flooded. So you have a change in ecosystem upstream, and then there's not as much water downstream. So you get a shift, okay? You reduce river floodplains downstream from receiving those nutrients that come with flooding because the dam can control how much water comes through. They can cause thermal pollution. If they release too much water at a time, the water in the reservoir tends to be colder than the water down below the dam, downriver from the dam. So you can have water that's too cold. If you release too much cold water in, you can send fish into thermal shock. And then the other one that we've talked about, fish like salmon are going to swim upstream to spawn. They can't swim upstream if there's a storage dam across the river, okay? So they put in fish ladders to help that. It's got less room for expansion because really, if you look at it, the big rivers in the world that could be used for hydropower are already being used for hydropower. So it's really there's not that much room for growth. You can't really add too much to it. So there are newer renewables, perfect segue to the end, that we're going to talk about in the next chapter that give us a whole lot more room for growth. So there we go. Those are our conventional alternative energy sources.